Welcome to Ultimate Sleep Doctor. Tonight, we journey to places far beyond our own world. We'll be exploring the atmospheres of exoplanets, distant worlds circling other stars, each a unique and silent mystery. These are realms of gas and light, potentially holding secrets to the formation of planets, and perhaps echoes of processes so different from our own. It's a humbling thought, isn't it? To consider the vastness, the quiet grandeur of a universe teeming with possibility. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe. Let your thoughts drift. Let's begin. Let's embark on a journey to uncover secrets hidden amongst the stars, a quest to understand the atmospheres of planets circling distant suns. This isn't a mission of rockets and spaceships, but one of incredibly sensitive telescopes and clever detective work. We're hunting for tiny clues, the faint fingerprints of gases, left behind by exoplanets as they pass in front of their host stars. This technique, known as transit spectroscopy, is how we're beginning to truly understand these faraway worlds. The fundamental idea is quite elegant. As an exoplanet drifts across the face of its star, it blocks a tiny amount of the star's light. But this isn't just any light that's blocked. It's the light at specific wavelengths, certain colors, that are absorbed by the planet's atmosphere. Think of it like holding a colored glass over a bright lamp. The light passing through the glass would be tinted with the glass's color. Similarly, an exoplanet's atmosphere absorbs certain wavelengths of starlight, leaving gaps in the spectrum that reveal its composition. The Hubble Space Telescope, a veteran of space exploration, played a crucial role in the early days of this field. It's equipped with a spectrograph, an instrument that splits starlight into its constituent colors, much like a prism. As a planet transits, Hubble observes the star's light before and after the planet passes in front of it. By comparing these two spectra, astronomers can identify the wavelengths that have been absorbed by the planet's atmosphere. For instance, a strong absorption feature at a particular wavelength suggests the presence of water vapor. Water vapor absorbs strongly in the infrared part of the spectrum, and Hubble's observations, particularly of the hot, massive Jupiter-like planet HD 209,458b, provided some of the earliest compelling evidence for atmospheric constituents. However, this technique isn't simple. The stellar light is incredibly bright, and the signals from the exoplanet's atmosphere are incredibly faint. Detecting these subtle differences requires meticulous data analysis and a deep understanding of stellar activity. Stars aren't quiet. They're constantly churning with magnetic fields, producing star spots, giant areas of intense darkness, and occasionally erupting in powerful flares. These events can dramatically alter the spectrum of the star, creating spurious signals that can mimic the presence of an atmosphere. It's like trying to hear a whisper in a crowded room. To combat this false positive problem, astronomers employ a rigorous series of tests. They start by carefully characterizing the host star's spectrum, looking for any stellar activity that might be influencing the data. They then analyze the transit light curve, the plot of the star's brightness as a function of time during the transit, looking for systematic variations that could be caused by stellar activity. Furthermore, they'll examine the spectrum for multiple absorption features, a signature that could point to a genuine atmospheric signal. Confirmation usually comes from observing multiple transits and obtaining multiple spectra. The arrival of the James Webb Space Telescope, JWST, has revolutionized the field. Unlike Hubble, JWST is primarily an infrared telescope. This is hugely advantageous for studying exoplanet atmospheres because water vapor, methane, carbon dioxide, key molecules in the search for potentially habitable worlds, absorb strongly in the infrared. Hubble's capabilities are still valuable, especially for observing cooler, larger exoplanets, but JWST's enhanced sensitivity and infrared focus provides a tremendous advantage, particularly when searching for biosignatures, indicators of life. Take, for instance, the observations of WASP 39b, a hot, puffy gas giant. JWST's infrared data revealed the surprisingly clear presence of water vapor in its atmosphere, along with tentative detections of methane and carbon dioxide. These observations allowed scientists to estimate the planet's temperature with greater accuracy than previously possible. Similarly, the TRAPPIST-1 system, featuring 7 Earth-sized planets orbiting a red dwarf star, has been a focus of intense study with JWST. The data suggests that TRAPPIST-1e, in particular, possesses an atmosphere rich in water vapor, potentially making it a prime candidate for further investigation. The data processing pipeline itself is a complex and lengthy undertaking. Raw data from the telescope requires extensive calibration, removing instrumental artifacts, and correcting for atmospheric absorption. Noise reduction techniques, such as averaging multiple measurements, are employed to enhance the signal-to-noise ratio. Scientists meticulously model the expected stellar spectrum and compare it to the observed data, accounting for the star's activity and the planet's transit. Looking ahead, the future of transit spectroscopy is bright. Planned upgrades to Hubble, along with the continued operation of JWST, promise even more precise measurements. New instruments, designed specifically for exoplanet atmospheric characterization, are also under development. These instruments will incorporate advanced techniques such as coronagraphs, devices that block out the star's light completely, to further reduce the noise and allow for even more sensitive measurements. Ultimately, the quest to understand exoplanet atmospheres is a testament to human ingenuity and our desire to explore the universe beyond our solar system. Each transit, each spectrum, brings us closer to answering one of the most fundamental questions: are we alone? The data gathered through transit spectroscopy is gradually painting a vibrant picture of these distant worlds, and with each new observation, the story of the universe becomes a little bit clearer. Let's delve into the fascinating world of atmospheric retrieval, the art of turning a faint, distant spectrum of light from an exoplanet into a detailed picture of its atmosphere. It's like being a cosmic detective, piecing together clues to understand what's happening high above the surface of a world orbiting a faraway star. The data we gather from telescopes like JWST provides a smeared, blurred fingerprint of the planet's atmosphere. And the goal of retrieval modeling is to sharpen that fingerprint, revealing the underlying composition and temperature. At its core, atmospheric retrieval relies on incredibly complex mathematical models. These models describe how light interacts with the gases within an atmosphere. The fundamental equation governing this interaction is the radiative transfer equation. It essentially says that as light travels through the atmosphere, Some of it is absorbed by the gases, particularly when the light's wavelength matches the energy needed to excite an atom or molecule. The absorbed light is then re-emitted, creating a spectrum that we observe from Earth. The equation accounts for factors like the density of the gases, their absorption strengths, and the geometry of the light's path through the atmosphere. To solve this equation efficiently, especially for the complex geometries of exoplanetary atmospheres, astronomers use sophisticated methods like LORAX, the line-of-sight radiative transfer algorithm executor. LORAX quickly calculates the spectrum that would be produced by a given set of atmospheric parameters, things like temperature, pressure, and the abundance of different molecules. It does this by breaking the line of sight through the atmosphere into many tiny steps, repeatedly applying the radiative transfer equation at each step. This creates a vast, simulated spectrum. The process of atmospheric retrieval then becomes an iterative optimization problem. We start with an initial guess for the atmospheric parameters. The algorithm compares this simulated spectrum to the observed spectrum from JWST. The difference between the two is quantified as a chi-squared value. A smaller chi-squared indicates a better match. The algorithm then adjusts the atmospheric parameters, temperature, pressure, molecule abundances, to minimize the chi-squared value, effectively making the simulated spectrum as closely resemble the observed one as possible. This process is repeated many times, each time refining the atmospheric parameters. A powerful technique used to handle the complexities and uncertainties inherent in this optimization process is Markov Chain Monte Carlo, MCMC. MCMC doesn't provide a single, definitive answer. Instead, it generates a probability distribution of possible atmospheric parameters, reflecting the uncertainties in our measurements and the assumptions made in the model. Imagine a vast landscape of possible atmospheres, and MCMC allows us to explore this landscape, identifying regions where the model best fits the data while acknowledging the inherent uncertainties. It's like a sophisticated search algorithm, exploring all plausible solutions within the constraints of the model. Of course, the accuracy of atmospheric retrieval depends heavily on the assumptions we make. For example, we need to estimate the amount of cloud cover. Are there high-altitude clouds reflecting sunlight or low-level clouds absorbing it? We also need to account for the presence of aerosols, tiny particles suspended in the atmosphere that can scatter and absorb light. Accurately determining the spectral line shapes of the molecules themselves is also crucial, as these shapes are affected by factors like temperature and pressure. Even slight errors in these assumptions can lead to significant biases in the retrieved results. Let's consider the case of GJ 1132b, a hot Jupiter, a gas giant orbiting extremely close to its star. This planet is constantly bombarded with intense radiation, which creates complex chemical reactions in its atmosphere. Modeling this highly irradiated environment is particularly challenging. The abundance of molecules like water vapor, which is a strong absorber of infrared light, is heavily influenced by the stellar flux. Retrieving accurate temperature and composition information from GJ 1132b's spectrum requires careful consideration of these photochemical effects, often necessitating the use of sophisticated atmospheric chemistry codes like CHEMPATH or ATMO. which simulate these complex reactions. Another significant source of uncertainty comes from stellar spectral contamination. The light from the star itself bleeds through the planet's atmosphere, creating a background signal that can mask the planet's spectral features. Subtracting this stellar contamination is a critical step in the retrieval process, and the accuracy of this subtraction directly impacts the retrieved atmospheric parameters. Sophisticated techniques are employed to model the stellar spectrum and remove its contribution, but this process is never perfect. Different retrieval algorithms exist, each with its own strengths and weaknesses. Some algorithms are better suited for certain types of atmospheres, while others are more robust to uncertainties. The choice of algorithm often depends on the specific characteristics of the exoplanet and the data available. Researchers are constantly developing and refining these algorithms, aiming for greater accuracy and robustness. Ultimately, atmospheric retrieval is a testament to human ingenuity, a combination of sophisticated mathematical models, powerful telescopes, and careful analysis. It's a challenging but incredibly rewarding field, bringing us closer to understanding the diversity of atmospheres beyond our solar system, and perhaps even discovering signs of life. The atmospheres of hot Jupiters, planets circling incredibly close to their stars, are some of the most bizarre and fascinating places in our solar system, and indeed the galaxy. These giants, far hotter than our own Jupiter, have experienced a chemical transformation unlike anything seen in cooler, more distant planets. Their extreme temperatures, fueled by constant irradiation from their host stars, drive reactions at a furious pace, creating conditions where familiar molecules are shattered and entirely new ones can form. The energy input, primarily in the form of ultraviolet (UV) radiation, relentlessly breaks apart molecules like water and carbon dioxide, initiating a cascade of chemical events. Let's consider the fate of water. When bombarded with UV light, water molecules, H2O, are ripped apart, creating hydrogen atoms and hydroxyl radicals, OH. The hydroxyl radical is a particularly reactive species, immediately snatching up other molecules and initiating a complex chain of reactions. Simultaneously, carbon dioxide also undergoes photolysis, breaking into oxygen and carbon monoxide. These are the building blocks for a whole host of other compounds. The key here is that the energy from the star isn't just heating the planet. It's actively changing its chemical makeup. The formation of ozone, O3, provides a captivating example. While ozone in Earth's atmosphere is a protective shield against harmful UV radiation, in a hot Jupiter atmosphere, the conditions are reversed. The intense UV radiation promotes the formation of ozone, but instead of shielding the surface, it's primarily found in the upper atmosphere, where the ozone concentration is highest. The ozone then acts as a catalyst, accelerating further photochemical reactions. These reactions aren't happening uniformly across the planet. Because hot Jupiters rotate incredibly rapidly, some complete a revolution in just a few hours, they experience a dramatic day-side-night-side temperature gradient. The day side, perpetually exposed to the star's intense radiation, is scorching hot, while the night side remains surprisingly cold. This temperature difference profoundly influences atmospheric composition. The hotter day side favors the formation of volatile compounds like methane and hydrogen, while the cooler night side might retain heavier, less volatile molecules. The possibility of complex organic molecules forming in these extreme environments is a topic of intense research. While the initial conditions seem hostile to the formation of life as we know it, the sheer energy available and the potential for novel chemical pathways are intriguing. Scientists have detected precursors to complex organic molecules, such as formaldehyde, CH2O, and hydrogen cyanide, HCN, in the spectra of hot Jupiters. These molecules are not, in themselves, signs of life, but they represent the fundamental building blocks that, under different conditions, could potentially lead to the formation of more complex organic compounds. The detection of these species relies heavily on sophisticated retrieval models, attempting to disentangle the myriad signals from the planet's atmosphere. However, modeling the chemistry of hot Jupiter atmospheres is an enormous challenge. These systems involve countless chemical reactions, often with multiple steps, each requiring specific temperatures and pressures. Moreover, accurately determining the rate constants for these reactions, how quickly they proceed, is incredibly difficult. Rate constants are sensitive to temperature, pressure, and the presence of other molecules, leading to significant uncertainties. Scientists employ sophisticated computer simulations, constantly refining their models and incorporating new observational data. Stellar flares, sudden bursts of energy from the host star, also play a significant role in modifying the composition of hot Jupiter atmospheres. These flares can inject vast amounts of energy and radiation into the planet's atmosphere, creating transient chemical species that would otherwise not be formed. These transient molecules, often short-lived, can dramatically alter the atmospheric spectrum, making it even more difficult to interpret. These flares are essentially chemical shock waves impacting the atmosphere. Comparing the chemical composition of hot Jupiters with that of solar-type giant planets, like Jupiter or Saturn, highlights the profound influence of stellar irradiation. Solar-type giants have evolved over billions of years, allowing for the gradual depletion of easily accessible volatile molecules through processes like atmospheric escape. Hot Jupiters, on the other hand, have experienced a far more rapid and dramatic transformation, largely due to the constant bombardment by their stars. Their atmospheres are often richer in heavier elements and compounds that would have been long, since processed away in a solar-type giant. Future observations, utilizing even more sensitive instruments like the James Webb Space Telescope, are expected to provide a much clearer picture of these complex atmospheres. As we continue to gather data and refine our models, we will undoubtedly uncover new surprises and gain a deeper understanding of the incredible chemical diversity that exists among the planets orbiting distant stars. The ongoing quest to decode the chemical fingerprints of these worlds is a testament to the power of scientific inquiry and our enduring fascination with the cosmos. The faint glow of distant stars paints the atmosphere of exoplanets with a complexity we're only just beginning to understand. While detecting the presence of water vapor and methane, as we've discussed, is a monumental achievement, truly deciphering the makeup of these worlds relies heavily on the invisible, their clouds, and the tiny particles suspended within them. These aren't fluffy white cotton balls like those on Earth. Exoplanetary clouds are formed through vastly different processes, sculpted by radiation and driven by conditions far removed from our own solar system. The formation of clouds in an exoplanetary atmosphere begins with condensation, the process where a gas transitions directly into a liquid or solid state. This doesn't require a phase change like boiling water. Instead, molecules cool to a point where they clump together, forming tiny droplets or ice crystals. The temperature and pressure within the atmosphere dictate the likelihood and type of condensation. For instance, on a planet orbiting a hot, young star like an M-dwarf, intense UV radiation can drive this process, creating layers of complex organic molecules through photochemical reactions. Conversely, in colder atmospheres, ice crystals are the dominant cloud formers. But clouds aren't just formed through simple condensation. Collision coalescence is a key process. As tiny droplets grow, they collide with and absorb smaller droplets, increasing in size until they become large enough to fall through the atmosphere, much like rain on Earth. Gravitational settling plays a crucial role here. Heavier particles are pulled downwards by the planet's gravity, accelerating their growth. The efficiency of these processes, collision frequency, gravitational acceleration, are highly dependent on the atmospheric conditions. Now let's talk about aerosols, those tiny suspended particles that profoundly influence how we see an exoplanet's atmosphere. These aren't just dust. They encompass a vast range of materials, each with unique properties. Silicate dust, released from the planet's surface through volcanic activity or impacts, scatters light, creating a hazy appearance. Organic haze, particularly abundant around M-dwarf stars, arises from the UV-driven photolysis of hydrocarbons, essentially, the breakdown of complex organic molecules. These hazes can be incredibly thick, significantly reducing the amount of light that reaches deeper into the atmosphere. Even sulfur dioxide, if present, can form aerosols that dramatically impact the transmission spectrum. Understanding how these aerosols interact with light is at the heart of what we call a gray atmosphere model. This isn't about a cloudy sky. It's a mathematical approach where we assume that the amount of light absorbed and scattered is the same at all wavelengths. It's a simplification, but it's a crucial starting point. Instead of trying to predict the exact amount of light at each wavelength, we focus on the overall opacity, the total ability of the atmosphere to block light. This is where radiative transfer codes come in. These sophisticated computer programs simulate the journey of radiation through the atmosphere, accounting for absorption and scattering by both the atmospheric gases and the aerosols. They're essentially miniature versions of the universe, letting us explore how light behaves within an exoplanetary environment. The results of these calculations are expressed as transmission spectra. Essentially, the amount of light that gets through the atmosphere to our telescopes. Because aerosols absorb and scatter light, the transmission spectrum will be noticeably different from what we'd expect if the atmosphere were entirely transparent. The shapes and features in these spectra are then used to infer the abundance and distribution of the aerosols, as well as the temperatures and pressures within the atmosphere. The infrared wavelengths are particularly sensitive to cloud and aerosol effects. Clouds are extremely efficient at absorbing radiation at these longer wavelengths, leading to a significant drop in the observed spectrum. Identifying and characterizing these absorption features is a primary goal in exoplanet research. Let's consider the atmospheres around M-dwarf stars. These smaller, cooler stars emit a much higher flux of UV radiation than our Sun. This intense radiation drives a runaway process of haze formation, leading to incredibly thick, opaque atmospheres, some of the densest we've ever observed. The haze layers significantly influence the observed transmission spectra, making it incredibly challenging to detect and characterize the underlying atmospheric composition. Models of these atmospheres need to account for not just the haze, but also the complex chemical reactions occurring within it. A case in point is the potential haze layers observed in the atmospheres of transiting planets around M-dwarf stars. Initial observations suggested a surprisingly hazy environment, prompting intense debate and further analysis. The thick haze fundamentally alters the way we interpret the data, demanding highly sophisticated models to disentangle the atmospheric components from the scattered and absorbed light. Ultimately, understanding exoplanetary atmospheres is a complex puzzle. It requires combining detailed observations with powerful computer models. The interplay between clouds, aerosols, and radiation is remarkably intricate, but with each new observation and refined model, we're steadily gaining a more complete understanding of these distant worlds. The quest to find life beyond Earth has taken a fascinating turn, shifting our focus from simply detecting planets to actively searching for the fingerprints of living organisms in their atmospheres. We've moved beyond the initial excitement of finding potentially habitable worlds and are now intensely investigating what those atmospheres might actually contain. The search for biosignatures, indicators that a planet might harbor life, is a monumental challenge, demanding both sophisticated observation techniques and a deep understanding of planetary processes. Oxygen, once considered the smoking gun for life, is now recognized as a far more complex story. While biological oxygen production is undoubtedly a potent biosignature, it's easily created abiotically through photochemical reactions, particularly in the upper atmospheres of planets exposed to intense ultraviolet radiation. The breakdown of water molecules, for example, can generate oxygen, and this process is entirely independent of any life. Therefore, a high concentration of oxygen alone doesn't definitively prove life exists. It simply indicates a potentially reactive environment. Instead, scientists are looking for a suite of molecules, each offering a different clue. Methane, for instance, is a gas produced by a variety of sources, including geological processes like serpentinization, where water reacts with rocks, and microbial methanogenesis, a process carried out by certain microorganisms. The presence of methane alongside oxygen is a compelling, though not conclusive, signal, as it suggests an ongoing, dynamic exchange between biological and geological processes. Similarly, nitrous oxide, N2O, is generated by microbial activity in soils and oceans, and its detection could point to biological activity, particularly in planets with liquid water. Then there's dimethyl sulfide, DMS, a fascinating compound produced almost exclusively by phytoplankton, the microscopic plants that form the base of aquatic food chains on Earth. Detecting DMS in the atmosphere of a planet with liquid water would be a strong indication of photosynthetic life, although again, the concentration and context are crucial. The sheer abundance of DMS, if observed, would provide an incredibly encouraging sign. Beyond these well-known possibilities, scientists are investigating other molecules like phosphine, which, if produced biologically, would represent a truly remarkable discovery. A significant hurdle in this search is the difficulty of distinguishing between biotic and abiotic sources. Planetary atmospheres are incredibly complex, constantly being shaped by interactions between sunlight, atmospheric gases, and surface processes. Understanding these interactions, termed atmospheric chemistry, is paramount. Computer models are being developed to simulate these reactions, attempting to predict the likely atmospheric composition based on various planetary conditions. These models, however, are constantly being refined and challenged as new observations are made and our understanding of planetary processes grows. Searching for biosignatures isn't just about identifying individual molecules. It's about looking for patterns in atmospheric composition. For example, detecting a continuously replenished supply of a gas, rather than a transient spike, would be a more compelling indicator of life. Furthermore, the ratios of different gases can be incredibly informative. A specific ratio of methane to carbon dioxide, for instance, could be a signature of a particular biological process. A particularly promising avenue of research is focused on detecting the signatures of photosynthesis. This would involve searching for combinations of gases, such as oxygen, methane, and carbon dioxide, that are characteristic of this process. Detecting spectral features related to chlorophyll, the pigment that captures sunlight in plants, would be a game changer. Terrestrial exoplanets, especially those orbiting red dwarf stars, are prime targets in this effort. The challenge here lies in interpreting the spectral signatures, as other pigments and molecules can mimic the signals of chlorophyll. New detection techniques are being developed to improve our ability to identify biosignatures. Future telescopes, like the Extremely Large Telescope, ELT, and the James Webb Space Telescope, will be capable of measuring the composition of exoplanet atmospheres with unprecedented precision. Furthermore, scientists are exploring the use of coronagraphs, instruments that block out the light from a star, to directly image the atmospheres of exoplanets, avoiding the confounding effects of stellar contamination. The ethical implications of detecting life on other planets are profound and deserve careful consideration. What responsibilities would we have to a newly discovered extraterrestrial ecosystem? Would we have the right to interfere with its development? These are questions that scientists, policymakers, and society as a whole must grapple with as we continue this extraordinary journey of exploration. The potential for both wonder and disruption makes this search a truly pivotal moment in human history. Ultimately, the quest for life beyond Earth is not just a scientific endeavor. It's a profound philosophical one, forcing us to reconsider our place in the cosmos. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. We've journeyed through the distant atmospheres of exoplanets, vast and silent. Let your thoughts now drift, calm and unhurried, like stardust settling into the velvet dark. Good night.